These are the answers to the AP Chemistry packet on topics 4.1 to 4.4. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. Question 1 says, a beaker contains 50 milliliters of a clear, colorless liquid. A student added a small amount of 1.0 molar aqueous sodium chloride to the liquid in the beaker. Which of the following is most likely to support the claim that a chemical reaction occurred in this experiment? On this slide, we can see several essential knowledge statements from the AP Chemistry course and exam description covering topics 4.1, Introduction for Reactions, and topic 4.4, Physical and Chemical Changes. Let's take a look at this essential knowledge statement, which talks about a chemical change. It says, a chemical change occurs when substances are transformed into new substances, typically with different compositions. Production of heat or light, formation of a gas, formation of a precipitate, and or color change provide possible evidence that a chemical change has occurred. Let's use this information to analyze choices A through D in this question. Choice A says the final volume of the mixture is 51 milliliters. And if we are combining a 1 molar solution of aqueous sodium chloride with 50 milliliters of a clear colorless liquid, then the total volume of the mixture should increase, but this is not necessarily an indication that a new substance has been produced. So we can eliminate choice A. Now let's take a look at choice D. It says the concentration of the aqueous chloride ion in the mixture is less than 1.0 molar. So if we start with a 1.0 molar aqueous solution of sodium chloride, and then we add that to 50 milliliters of liquid, the total volume of the mixture is going to increase, and that would be diluting the sodium chloride solution. So the concentration of sodium chloride would decrease. The concentration of chloride would be less than 1 molar, but just diluting the solution is not necessarily evidence that a brand new substance is produced. So we can eliminate choice D. Now let's take a look at choice C, which says the mixture conducts electricity. Sodium chloride is an ionic compound, and when it's dissolved in water, it behaves as an electrolyte. The positive sodium ions and the negative chloride ions can move freely throughout the solution. So if aqueous sodium chloride can conduct electricity, then in choice C, the mixture conducts electricity. That's already true about a solution of aqueous sodium chloride. So that's not evidence of a brand new substance being produced. So we can eliminate choice C. So why is the correct answer to question 1 choice B? Well, it says the appearance of the mixture is cloudy. And one of the possible signs that a new substance is produced in a chemical change is the formation of a precipitate. So a cloudy appearance of the mixture might be evidence of the formation of a precipitate. So the correct answer to question 1 is choice B. Now let's take a look at question 2. In question 2, we see a diagram with a beaker on a hot plate. It says a sample of pure liquid methanol, CH3OH, was added to a beaker and placed on a hot plate. The temperature of the liquid increased gradually. Eventually, the liquid began to produce bubbles vigorously. 4 diagrams are shown below to indicate a particulate representation of the gas produced above the surface of the liquid in this experiment. Which diagram best supports the claim that this experiment is a physical change? Let's take a look at that slide with the essential knowledge statements for topics 4.1 and 4.4, and let's focus on physical changes. So this first essential knowledge statement says, a physical change occurs when a substance undergoes a change in properties, but not a change in composition. changes in the phase of a substance, solid, liquid, gas, or formation, separation of mixtures of substances are common physical changes. So in this experiment, we're looking for a change in phase from a liquid to a gas, but not a change in composition. Now, we already know that the formula of methanol is CH3OH. So if all we're doing is changing it from a liquid to a gas, then the formula of the gas should still be CH3OH. And looking at these four particle diagrams, the only particle diagram that shows the molecules CH3OH in the gas phase above the surface of the liquid would be choice D. You can see molecules of CH3OH, but in choices A, B, and C, those are different substances that have different chemical composition. So we're looking for a physical change, no change in the composition of methanol. That's why the correct answer for question 2 is choice D. Now, let's take a look at question 3. It says a sample of solid sodium metal, so Na solid, is added to a sample of liquid water, H2O liquid. A chemical reaction occurs, and bubbles of hydrogen gas, H2 gas, are produced. After the reaction has gone to completion, the reaction mixture appears clear and colorless. Which of the following is the balanced net ionic equation that best represents the reaction that occurs in this experiment? Now, it's important to understand that when you are looking at a chemical equation and trying to decide if it's balanced or not, you have to consider both the atoms and the overall charge. So a chemical equation should be balanced in terms of the atoms and the overall charge. Let's start with choice A. In choice A, I see the same number of atoms of sodium and hydrogen on both the left and the right side of the equation. So it is balanced in terms of atoms, but it is not balanced in terms of the overall charge. If we look at the total charge on the left side of the equation, it has a charge of +2 because there are 2 H+ ions. And on the right side of the equation, the total charge is +1 because we have 1 Na+ ion. So therefore, because it's not balanced in terms of the overall charge, we can eliminate choice A. Now, let's take a look at choice D. So when I look at the left and the right side of the equation, I see the same number of atoms of sodium, hydrogen, and oxygen on both sides. So that equation is balanced in terms of atoms, but again, it's not balanced in terms of the overall charge. On the left side of the equation, we have 2 Na+ ions. That's a total charge of +2. But on the right side of the equation, there is no charge. There are no ions, and the total charge is 0. So because that equation is not balanced in terms of the overall charge, we can eliminate choice D. Now let's take a look at the difference in the chemical equations for choices B and C. In choice B, we see NaOH, that's sodium hydroxide, appearing on the right side of the equation in solid form. And in choice C, we also see sodium hydroxide, but it appears in aqueous form, and it's split up into separate sodium ions and hydroxide ions. So is a solid product produced in this experiment, or is it an aqueous solution? If we take a closer look at the description of this experiment, it says, after the reaction has gone to completion, the reaction mixture appears clear and colorless. So if the reaction mixture appears clear and colorless, that means that there would not be a solid product produced, so we can eliminate choice B. So the correct answer for number 3 is C. And just to verify, this chemical equation should be balanced in terms of both the atoms and the overall charge. So in choice C, we see the same number of atoms of sodium, hydrogen, and oxygen on both sides of the equation, and the total charge on the left is 0, and the total charge on the right is also 0. So question 3, the correct answer is choice C. Now, let's take a look at question 4. Question 4 says, when solutions of barium nitrate and potassium carbonate are combined, a solid precipitate is formed. Which of the following is the balanced net ionic equation for the reaction that occurs when these two solutions are combined? So the first thing I'm going to do is try to write the correct chemical formulas of the products of this chemical reaction. So my first reactant is barium nitrate, and I know from where barium is located on the periodic table in group 2 that barium has a charge of +2. I can see in this formula of barium nitrate that there are 2 nitrate ions for every 1 barium ion, and I know that the charge on the nitrate ion, NO3, is -1. The next reactant is potassium carbonate. I know from its position on the periodic table, potassium is in group 1, so it has a charge of +1, and in this formula there are 2 potassium ions for every 1 carbonate ion. So the charge on the carbonate ion is -2. This is very important because when I write the chemical formulas of the products of this chemical reaction, I have to pay attention to the charges of the ions. So barium is now going to be combined with the carbonate ion, and the formula of barium carbonate is BaCO3, and the charges on those 2 ions cancel each other out. The other product of this chemical reaction is potassium nitrate, and the charge on potassium and nitrate, they cancel each other out, so the formula of potassium nitrate is KNO3. Now, in order to balance the overall chemical equation, I do need to add a coefficient of 2 in front of the potassium nitrate. In other words, to balance the total number of potassiums on the left and the right, and the total number of nitrate ions on the left and the right, there's going to be a 2 as a coefficient in front of the potassium nitrate. So here is my balanced equation for this chemical reaction. You'll notice that I have aqueous for barium nitrate on the left, and I have aqueous for potassium carbonate on the left. But on the right side of the equation, I've put question marks for the moment because it says a solid precipitate is formed. I have to determine which one of these products is in fact the solid precipitate. You may remember from an earlier video in topic 4.2, which was on net ionic equations, I taught you this acronym, which is called SNAP. So one way to remember these soluble ions, the soluble SNAP ions, is sodium, nitrate, ammonium, and potassium. So those are soluble. The fact that potassium nitrate contains one of those soluble SNAP ions means that potassium nitrate is soluble. That's going to be aqueous, so therefore my solid precipitate is not potassium nitrate, but in fact barium carbonate. So now I've balanced the equation and I've identified that the precipitate is barium carbonate. Let's take a look at the 4 choices in question 4. Starting with choice A, I can see that on the right side of the equation, they're showing barium carbonate as aqueous and potassium nitrate as solid. So we know that's not correct. Barium carbonate is the solid precipitate and potassium nitrate is going to be aqueous, so we can eliminate choice A. In a similar fashion, we can eliminate choice C because it shows that potassium nitrate is in solid form. But we know that potassium nitrate is soluble and aqueous, so we can eliminate choice C. Now we've narrowed it down to choices B and D. Let me remind you, from an earlier video I talked about the difference between a molecular equation, in which each reactant and product is written as a neutral compound, and a net ionic equation, which is what you get after you eliminate the spectator ions from both sides of the complete ionic equation. So here on the next slide is an example of a question I talked about in an earlier video. This is similar to the chemical reaction that's happening in question 4 in this packet. So we have a barium chloride, which I'm going to split up into separate barium and chloride ions. We have a potassium sulfate, which I will also split up into separate potassium and sulfate ions. But on the right side of the equation, we see that barium sulfate, or BaSO4, is written as a solid precipitate. So we don't split up the precipitate into separate ions because it's not soluble, it's not dispersed throughout the solution. It's sitting at the bottom of the beaker or the test tube as a solid precipitate. But if KCl, potassium chloride, is aqueous, then I would split that up into separate ions. So again, this is not the specific reaction that we're looking at in question 4 of this packet, but it's similar, and I can use it as an example. Let me go ahead and cross off the spectator ions from both sides of the equation. That would be the chloride ions and the potassium ions. And now you can see the net ionic equation, which is the formation of solid barium sulfate. Now, let's go back to question 4, and we can see that in choice B, we're looking at the balanced molecular equation, but in choice D, we're looking at the balanced net ionic equation after the soluble potassium ions and nitrate ions have been eliminated as spectator ions from the equation. So the correct answer to question 4 is D, because it's showing the balanced net ionic equation. Choice B is not the correct answer because that would be the molecular equation. So the answer to question 4 is D. Now let's take a look at question 5. Question 5 says hydrochloric acid, HCl, is an example of a strong acid that completely ionizes in aqueous solution according to the equation shown above. A student adds an excess amount of aqueous hydrochloric acid to a sample of solid sodium carbonate, Na2CO3, solid. A chemical reaction occurs according to the equation shown below. Which of the following is the balanced net ionic equation for the reaction that occurred in this experiment? So the strategy for answering question 5 is to take a look at each one of the substances in this balanced chemical equation and decide, should that chemical formula be written exactly as is, or should we split it up into separate ions? Let's start with the sodium carbonate, Na2CO3. We're not going to split up sodium carbonate into separate ions because it appears in solid form. So a solid ionic compound is not going to be broken up into separate ions. So we're going to just go ahead and write sodium carbonate exactly as it appears, Na2CO3 solid. The next chemical is the hydrochloric acid, which we were told is an example of a strong acid that completely ionizes in aqueous solution. So for the hydrochloric acid, we are going to split it up into separate ions. And there is a 2 in front of the formula HCl. So when we split up the hydrochloric acid, it'll be split up into 2 aqueous H plus ions and 2 aqueous Cl minus ions. Now let's take a look at the chemicals on the right side of the equation. The first one is sodium chloride. Now it's already in aqueous form. We know that sodium is one of those 4 soluble snap ions. We know it's soluble. It's definitely going to be split up into separate ions. So for aqueous ionic compounds, they'll be split up into separate ions. I see a 2 in front of the NaCl. So when I split it up, it'll be 2 Na plus ions that are aqueous and 2 Cl minus ions that are also aqueous. Now we come to the last 2 chemicals on the right side of the equation, and that would be liquid water and carbon dioxide gas, CO2. But we're not going to split these up into separate ions because they are either a pure liquid or a gas, so they're going to remain exactly as written. So we don't split up the water, it'll just be written as H2O liquid, and we don't split up the CO2, just CO2 gas. Now, do we see any examples of spectator ions that appear on both the left and the right side of the equation? If we do, we can cross off the spectator ions on both sides. So I see 2 chloride ions on the left, and I see 2 chloride ions on the right. Okay, we've crossed off our spectator ions. Now, what remains is the correct answer to question 5. We're looking for the net ionic equation, and so that would correspond to choice A. solid sodium carbonate, Na2CO3, plus 2 aqueous H plus ions produces 2 aqueous Na plus ions, along with water, liquid water, and CO2 gas. So the correct answer for question 5 is choice A. Now let's take a look at question 6. Question 6 says a sample of solid copper is added to a sample of aqueous silver nitrate, AgNO3, as shown in the diagram above. A chemical reaction occurs, resulting in the formation of solid silver. At the end of the experiment, the reaction mixture contains aqueous copper 2 plus ions. Which of the following is a balanced equation that represents only the species that react and the species that are produced in this experiment? So we know the reactants in this experiment are solid copper and aqueous silver nitrate, AgNO3. And the products that are formed in this experiment are solid silver and aqueous copper 2 plus ions. So the reactants are solid copper and aqueous silver nitrate, and the products are solid silver and aqueous copper 2 plus ions. Now you might be wondering, if there are nitrate ions present on the left side of the equation, shouldn't there be nitrate ions present on the right side of the equation? And the answer is yes. What's in that beaker at the end of the experiment is not only copper 2 plus ions dissolved in that solution, but also the nitrate ions are still present, dissolved in that solution at the end of the experiment. So I'm going to write the formula of the product copper 2 nitrate. And the formula of copper 2 nitrate would be Cu, and then parentheses around the NO3 with a subscript of 2. In other words, there are 2 nitrate ions for every 1 copper ion in that chemical formula. Now, right now this equation is not balanced because I have 2 nitrate ions on the right and I have only 1 nitrate ion on the left. So I'm going to put a coefficient of 2 in front of the formula for silver nitrate, but then I have to also put a 2 in front of the silver on the right side of the equation. Okay, so now this equation is balanced. Let's go back and look at the 4 choices, A, B, C, and D, for question 6. It does say which of the following is a balanced equation that represents only the species that react and the species that are produced in this experiment. That's another way of saying write the net ionic equation for the reaction that occurs in this experiment. So even though choice B looks like it could potentially be the correct answer, the problem is that the nitrate ions were not reacting and they were not produced. The nitrate ions are simply present in solution the entire time. So nitrate ions do not react, nitrate ions are not produced, they are spectator ions. Let's go back and take a look at this equation. I'm going to split up anything that is an aqueous ionic compound into separate ions. So on the left, I see aqueous silver nitrate. I will split that up into silver ions and nitrate ions. And because there is a 2 as a coefficient in front of the AgNO3, when I split that up, it will be 2 Ag plus and 2 NO3 minus. And on the other side of the equation, I will split up the formula of the aqueous copper 2 nitrate into Cu2 plus ions and 2 nitrate ions. Now, hopefully you can see that we have 2 nitrate ions on the left, and we have 2 nitrate ions on the right. So the nitrate ions are not reacting, they're not being produced, they simply were present the entire time in this experiment, and I can cross them off as spectator ions on both sides of the equation. So what I am left with is the net ionic equation. And so the net ionic equation for what actually happened in this experiment is that solid copper reacted with aqueous silver ions to produce solid silver and aqueous copper 2 plus ions. Now let's go back and look at our 4 choices, A, B, C, and D. Let me see if I can explain why the incorrect answers are incorrect. I'll start with choice A. Now, the problem with choice A is that even though it's balanced in terms of atoms, in choice A, the equation is not balanced in terms of overall charge. There's a +1 charge on the left side of the equation, and there's a +2 charge on the right side. So we can eliminate choice A because the equation is not balanced in terms of overall charge. We can eliminate choice B because even though it is a correctly balanced equation, nitrate ions did not react, nitrate ions were not produced, so the nitrate ions are spectator ions and they should be eliminated from the overall equation. So we can eliminate choice B. And now taking a look at choice D, even though it is balanced in terms of atoms and charge, the reactant in this experiment is solid copper, not copper 2+ ions. So that's the problem with choice D. It's got the wrong chemical formula on the left. It should be solid copper, not copper 2+ ions. It also shows silver ions on the right instead of solid silver with no charge. So we can eliminate choice D, and now we have the correct answer. The correct answer for question 6, which represents the net ionic equation, is choice C. It is a balanced equation, and it represents only the species that react and the species that are produced in this experiment. Now, let's take a look at question 7. Question 7 says a mixture of X2 and Y2 is placed in a reaction vessel as shown above. A reaction between X2 and Y2 occurs, forming XY2. Which of the following best represents the contents of the reaction vessel after the reaction has proceeded as completely as possible? So a good first step in answering this question is to write a balanced chemical equation for the reaction that takes place between X2 and Y2 to produce XY2. And so right now on this slide, we have an unbalanced chemical equation. To balance this equation, I need to put a 2 in front of the XY2 on the right side of the equation. And now I need to put a 2 in front of the Y2 on the left side of the equation. So now this equation is completely balanced. Now what I'm going to do is draw a box, which you can see in the upper right corner of this slide. And I will use this box to keep track of the contents of the reaction vessel as the reaction proceeds. So we know from the balanced equation that one molecule of X2, represented by the black circles, reacts with 2 molecules of Y2, represented by the gray circles. And you can see I've drawn a circle around that set of reactants, and it produces 2 molecules of XY2, which I'm showing in the particle diagram in the upper right corner of this slide. I'm going to do that one more time. I'm going to draw a circle around that set of reactants. So 1 molecule of X2 and 2 molecules of Y2. So that set of reactants would produce another 2 molecules of XY2. Now, if I stop right now, this particle diagram in the upper right corner of the slide looks like choice A in question 7. So you might be thinking that choice A is the correct answer. But the problem is I still haven't accounted for all of the contents of the reaction vessel. So now that the reaction looks like it's finished, there still is an unreacted molecule of X2. There's 1 more molecule of X2 that's left over, excess, and should still appear in the reaction vessel at the end of the experiment. So what you see in the upper right corner of this slide, that is the correct answer to question 7. So what I'm looking for is a particle diagram that contains the following: 4 molecules of XY2 and 1 molecule of leftover or excess X2. And what that would correspond to is choice D. So choice D is the correct answer, which contains 4 molecules of XY2, plus 1 molecule of unreacted X2. So D is the correct answer to question 7. Now let's take a look at question 8. Question 8 says, the particle level diagram shown above is a representation of the substances present in a reaction vessel at the completion of a reaction between QX and X2. Which of the following diagrams represents the reaction mixture that would yield the product mixture shown above? So, unlike question 7, where we were going from a reactant mixture to a product mixture, here in question 8, we're going in the opposite direction. We are given a product mixture, and we have to go backwards to the reactant mixture. So we do have a balanced chemical equation for this reaction, and what I'm going to do is take that balanced chemical equation and multiply each and every coefficient by 2. And I have a specific reason for doing this, which I will explain in just a moment. So here right now are the coefficients for this balanced chemical equation. And from left to right, the coefficients are 2, 1, and 2. So I'm going to multiply each of those coefficients by 2. So now the coefficients are 4, 2, and 4. And the reason why I did that is because take a look at the right side of the equation. I have in the particle diagram that I'm given 1, 2, 3, 4 molecules of the product QX2. So that represents the product of this experiment. 4 molecules of QX2 are visible in this particle diagram. That means that it would have come from the reactants that you see on the left side of the equation. So the reactants that would have produced 4 molecules of QX2 are the following. 4 molecules of QX, which I'm going to represent in that particle diagram in the upper left corner of this slide, and 2 molecules of X2. Now, if I stop right now at this point, you might think that the answer to question 8 is choice A. Because in choice A, you see 4 molecules of QX and 2 molecules of X2. The problem is I didn't take into account that there are still 2 extra molecules of unreacted X2 in the reaction vessel at the end of this experiment. So I can't ignore those extra 2 molecules of X2. They are still present at the end, which means they would have been present at the beginning. So I'm going to throw 2 more molecules of X2 into my particle diagram. And what you see in the upper left corner of this slide, that is the correct answer that I'm looking for. I'm looking for a particle diagram that contains the following molecules: 4 molecules of QX and 4 molecules of X2. That reactant mixture would have produced the product mixture that we were given. So the correct answer to question 8 is not A. The correct answer is choice B. Choice B is the correct answer, which contains 4 molecules of QX and 4 molecules of X2. Now, let's take a look at question 9. Question 9 says, based on the information in the particle diagrams above, which of the following represents the correct balanced chemical equation for the reaction that occurred? Let's focus our attention on the reactant mixture. So in the reactant mixture, we see substance A represented by white circles. And those are individual circles of A. They're not 2 atoms touching each other to make a molecule. They're individual white circles by themselves. So these reactant particles of A should be written as single A and not A with a subscript 2. So looking at our 4 choices, A, B, C, and D, we can eliminate choices C and D because they show the reactant as A2 instead of A. So I'm going to eliminate choices C and D. Now let's focus on substance X, represented by the black circles. There are 2 black circles touching each other, so these reactant particles should be written as X subscript 2, or molecules of X2, and not individual atoms of X. So looking at our two remaining choices, we can eliminate choice A because it shows X by itself instead of X with a subscript of 2. So I'm going to eliminate choice A. So the correct answer to question 9 is choice B. It shows that for every 2 atoms of A that react with 3 molecules of X2, 2 molecules of AX3 are produced in this chemical equation. So the answer to question 9 is choice B. So question 9 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.